Good afternoon, everyone. My name is Xiao. I'm a grad student from Worcester Polytechnic Institute. Today, I'm going to be presenting our project MARAS, Signaling Multidrug Adverse Reactions. These are all the authors of this paper: myself, Tabassum, Sasmisa, Alka from WPI, and Lei is from MIT. So just want to give you a heads up of the content of this talk. First, I'm going to be talking about some background, what is the multi-drug adverse reactions problem in general, how regulatory agencies like Food and Drug Administrations respond to these cases, what is the typical ADR reviewing and evaluation process, and I will discuss what is the problem in this process which leads to our project. And second, I will introduce our approach. In this 20 minutes talk, hopefully I give you the general idea and what is the intuition behind it. And last but not least, I will go over a few evaluation results and also some case studies. So what is adverse drug reactions? So an ADR is an unexpected reactions due to taking one or multiple drugs. It could be a very serious injury. As a matter of fact, ADRs are one of the leading causes of death in the United States. And back in 2000, in this year alone, there are more than 2 million serious ADR in hospitalized patients, causing over 100,000 deaths annually. So this is really a problem that don't need any actual motivations. It's a pretty serious question. So in this project, we focus on multi-drug ADR. So it's very common that when you take drugs, you take multiple drugs at the same time. And this study indicates that approximately 30% of the elderly patients are taking 6 or more drugs at the same time. And when we look at the general populations, so over 30% of the adverse reactions are caused by drug-drug interactions. This is pretty significant. And here is an example. So taking warfarin and ibuprofen could lead to severe bleeding. So this is something we want to identify and present it to the drug safety evaluator. So how does the regulatory agency like FDA respond to these cases? So FDA had made a tremendous amount of efforts setting up this platform that allow people to submit their adverse reaction cases. And so who can submit these cases? It's almost everyone. So healthcare professionals, consumers, just like you and me can submit, and also product manufacturers. In fact, product manufacturers are required to submit any cases that they are aware of. So as you can see in these charts, so the volume grows bigger and bigger every year. So it's good in a sense that a lot of cases get exposed, so FDA can respond to these cases. They can do label changes or even withdraw those drugs from the market. But that also causes some problem because the reviewing capacity of FDA is sort of limited. And it's not that there exists some computation method that can replace the manual reviewing process. Actually, the manual reviewing process is quite complicated. Those are very experienced drug safety evaluator, and very often they also need to do some literature reviews on each cases. So then what is the typical reviewing and evaluation process? So every Monday, there will be a week-long collection of reports assigned to different group of safety evaluators. So each group sort of specializes on a certain type of drugs. And they will go case by case to do the review. There are some signals provided by the system that help them to prioritize their workload. So for example, what is the most frequent ADRs this week or last week? What is the most frequent drugs appear in the database this week? This kind of signal help them to form their hypothesis. So what is the potential problem in this set of reports. And also, the original reports will be linked to these numbers. So when we observe this process and also talk to the safety evaluator, so one of the things we realize is there's no interaction signals that is supported by the system. So not that they don't have any tools to investigate it. So if they have something in mind, let's say they think drug A and drug B are interacting, and they have a tool that they can type in drug A and drug B, they will return some numbers based on other databases to see if there are interactions. But for this report, so once you have a set of reports, they don't have any signals. So that's exactly what we are trying to solve. So based on a collection of reports, we want to give them some indications of possible interactions. And more importantly, so when you generate the signals, it's always a must that you also provide the original reports that support the signals or indications. So this is the general framework of our system. So it starts with a set of reports, and it gets organized in the database, and then our system MARAS take a look at these reports and derive the signals from this set of reports and rank them, present it to the safety evaluator. So the safety evaluator can select the most interesting one, and they should be able to trace back to the original reports, because at the end of the day, the most important thing are the original reports. So for their proposal for label changes or a drug withdrawal, so the original reports are always attached in the proposal. So how can we derive such signals? So what information do we need? So in this project, we focused on two types of informations for each report. What are the suspected drugs, and what are the presented ADRs? There are more things to consider. So one of the things is time. Time information is quite important. That's something we currently exploring, but it's not in the scope of this project. So looking at this representations of the data, that reminds us associational mining. So as you may heard from yesterday's talk, so associational mining is a way of applying a relationship among the things or objects that occur together in a database. So if you apply this on that data sets, you can get a lot of rules like this: X imply Y, and X is a set of items, Y is also a set of items. In our context, X could be a set of drugs, Y is a set of ADRs. So looking at this, so one step for processing the association rule is you want to remove those irrelevant rules where you have ADRs on the left and drugs on the right, and so, also some sort of mixed rules. There are two classical measure to measure the significance of the rules. The first one is support. Support is essentially the proportion of the cases that contain X and Y. In this case, contain these three items. And the confidence is a conditional probability. So having X presented, having this drug presented, what is a possible? How possible you will have Y? So is it enough for us to send the signals to model the interactions? Apparently there are some problems. So one of the first thing is there's some misleading association rule. So let's consider a case. So imagine that you only have this one report in your database, and applying a traditional associational mining, you can generate actually 9 rules. Here, the minimum support and minimum threshold are 0. This is quite important that in our context, you have a very low threshold because every report counts. In our experiments, the minimum support is 15, so it's absolute value. So 15 cases is minimum support. So if in this extreme case, this minimum support is 0, so you will end up with 9 rules. But when you look at this rule, only one of them actually fully represent the original reports, which is the last one. So it says these 2 drugs are taken and 2 ADRs are presented, and nothing more and nothing less. So following these intuitions, we want to remove all those sub-rules, the upper ones, the other one out of the considerations. So we define 2 types of rule that we should be considered as signals. The first type is explicit supported rules. Simply, this is the exact situation as the example that I show. That if you have a rule and if there exists reports that show the exact same set of drugs and exact same set of ADRs, then this rule is explicitly supported. It's more safer to use as a signal. And the second type is slightly weaker. It's called implicit supported rules. The idea is it's okay you have a sub-rule, but as long as these sub-rules are an intersection of multiple reports. And to efficiently mine this, it turns out that, so mining frequent item sets is the first step of generating the association rule. So it turns out that mining this non-misleading rules is equivalent to finding closed frequent item sets. So following this, we are able to efficiently mine those signals. However, you still have a bunch of rules. So which one is more important? Which one is more interesting that align with the semantics of drug-drug interactions? So we propose a measure. The intuition behind this measure is ADR caused by interactions are only triggered by the combination, but not any individual drugs. So let's consider a case. So you have drug A and drug B, it triggers ADR1. And let's say you have a very high confidence, 90%. Does it actually say that drug 1 or drug 2 are interacting? Probably not. What if you have another rules, valid rules, that indicate that ADR1, drug 1 trigger ADR1 has confidence also has 90%. So it simply says the ADR1 has nothing to do with drug 2. Drug 1 alone can trigger ADR1. So here is 2 examples. The text on the top is the ADRs, and under the green bar are the complete set of drugs that consider trigger these ADRs. The size of the bar represents the confidence of this particular rule. So as you can see here, the green bar represents the rule that model the complete set of drug and the ADRs. The rest of the bar is the confidence of the rule that model any subset of the drugs with the ADRs. So ideally, we want a green bar as high as possible, but at the same time, the rest of the bar as low as possible. So in this case, the left case is more interesting because none of the individual actually triggered this ADR. On the right, where you have some single drug that can trigger these ADRs. So we propose a measure to reflect these points. Okay. So here is the generation process. First, we generate a frequent item sets and index in these adjacency letters, and we propose a bottom-up mining process that first identify the closed item sets and then generate a sub-rule to evaluate the final signals. For evaluations, we use the public version of FAERS. Available quarterly from 2013 to 2015. The reason is this is for the reproducibility of the paper, so everyone can try out this method and see the results. The first experiment I want to show is how many rules we can reduce from applying traditional associational mining. The first bar represents the number of rules generated by the traditional associational mining, and the second bar represents the number of relevant rules, meaning that you remove all those rules that has ADR on the left, drugs on the right. And third one is the number of rules with the misleading rules removed. So you end up with much fewer rules. This scale is log scale. And also we measure the accuracy. So we use precision at K because when a safety evaluator look at our results, is almost they won't look at, let's say, the signal ranked the thousandth. So they always want to look at the top results, maybe top 10 or top 20. So precision at K is a quite important measures. And to measure these results, we use it's not some claim or statement from the FDA. It's essentially from external sources. There's evidence that this set of drug test interactions, we use that as a ground truth. And this is the top 5 signals of 2015 and third quarters. So the first 2 methods are confidence and reporting ratios. The figure just want to show you that without removing any misleading rules, you end up with a lot of similar signals, and some of them are misleading. So as you can see, MARAS can generate a more diverse set of signals. And as shown in the previous experiment results, it's pretty accurate. And also we conduct some case studies. So all of these case studies, we find out that some of the top ranked signals, for example, this ranked the 2nd place, but in all the baseline method, they can rank 1,000 or even 10,000 positions. And this is a case where you have aliquots interact with ibuprofen. It's ranked 2nd in 2014 Q2 datasets. And this is a case where you have ondansetron and lithium. This is actually ranked 1st in the 2014 Q3 datasets. And this is third case study we have is Amplify and with ramipril. It's ranked 1st by MARAS in 2015 Q3 datasets. So in sum, in this work, we have, so we try to identify what is the misleading signals if you apply association rule in this context. And then we propose a measure to quantify the significance of these signals that align with the drug-drug interactions. Third, we evaluate the effectiveness of our system using real-world data sets. And I want to acknowledge Dr. Monty Hall, who was with FDA, and Saranjan Day with FDA for assisting us with the FAERS system. And this project is partially supported by NSF. The author, Susmita, is supported by IES. Mia and Tabassum are supported by ORISE Fellowship hosted by FDA. So thank you for listening. Any questions?